6, 7, 8, 9, 10, 11, 12, 13, 14.
Who are we missing? 6, 7, 8.
Oh, yeah, Kyla. See? All right.
Okay, so just to kind of wrap up our little quick review of logs. Why is that thing down there? Oh, it's frozen. That's why. Okay, so from the other day, remember we talked about what it means if we want to calculate the inverse of a function. All we do is swap x and y and solve for y, right? And we looked at a couple examples. These are just our notes from the other day, where we took an easy one. We took a line, y equals 3x plus 2, and if we went through that process, flip x and y, solve for y, we ended up getting x minus 2 over 3, right? Just a different line. Okay, but those two would be, they would have, what kind of symmetry would they have if they're inverses? Yeah, they would have folding symmetry or reflective symmetry over the line y equals x. And then we looked at a couple more. We tried f of x equals x squared, right? And so I asked you the question is, I just asked you the question, is g of x equal to the square root of x? Is that equal to its inverse? Are they inverse functions? Because it seems like they are, right? If I were to call this y, and then I flip x and y, and solve for y, you might think I'm just going to get the square root of x, right? And so is that my inverse function? And we tried it. But remember that the true definition of an inverse relationship is, whether it's a function or a non-function, it's just when you exchange the domain and the range, right? So what has the test to see if something is an inverse is if you take the function of its inverse, or the inverse of the function, and really that's kind of even a bad way to say it, because it's not like one of them is the inverse and one of them is the function. They're both functions, they're inverses of each other. So if we define f of x as one of the functions and g of x as the other, then if they are indeed inverses, f of g of x has to be x, and g of f of x has to be x. But when we try these, where f of x is x squared and g of x is the square root of x, f of g of x is x. So far, so good. But g of f of x gave us back the absolute value of x, which is not x. So it failed. And why was it that it failed? Well, we looked at the graphs. Y equals x squared, or f of x equals x squared, is a parabola, right? That is a function. It passes the vertical line test. But x equals y squared, if I graph that, I get a sideways parabola, which is a non-function, right? And so they aren't inverse functions. They're inverses, but one of them is not a function. And so you told me correctly, right, this is just a couple days ago, you told me correctly that we could have predicted that the inverse of the parabola would have failed the vertical line test because the parabola failed the horizontal line test. Okay, so if we put all this stuff together, we can use this to explore logs and exponentials, right? Logs and exponentials are inverses of each other, aren't they, right? If you look at the graph of the exponential function y equals e to the x and compare that to the logarithmic function y equals log x, sure enough, they have this reflective symmetry about the line y equals x. Both the logarithmic function and the exponential function are functions. So we're calling them functions for a reason. They both pass the vertical line test. But they also both pass the horizontal line test, right? So it's predictable that each one is going to have an inverse that is a function. Okay, so let's combine those two thoughts that we just had, right? We know that if we have two functions that are inverses, they have to do each other, or undo each other. So we have to get something like f of g of x equals x and g of f of x equals x, right? Okay, so if that's true then, and we can see that it is because these both pass the horizontal line test and the vertical line test, then we know that if I do the natural log, if we said like, for example, f of x equals natural log x and g of x equals e to the x, what would f of g of x look like? So I'm taking f of hand is just log of hand, right? So f of g of x would be log of hand, which is e to the x, right? So we're going to get the natural log of e to the x. What does that have to equal if they're inverses? X. Okay, so what's the moral of the story? A base e logarithm undoes a base e exponential, right? Now, I know that's pretty obvious, but I want to teach you to use that as an algebra step, right? Because rather than having to go back to our properties of logarithms and always write an equivalent statement when we want to solve for a log or an exponential, I think this is an easier way to do it, and I'll explain in a second. So what would g of f of x look like? G of hand is e to the hand. So e to the f of x, which is log x, must also equal, okay, so a base e exponential undoes a base e log also, it goes both ways. So why do I bring that up? So then if you wanted to, think back to pre-calculus here, if you wanted to solve an equation, like what if you wanted to solve the equation, something like, I'm just making this up, what if we had e to the 2x squared plus 1 equals 7. How did you guys do that? Okay, but it seems like, from what, and maybe it was different, but it seems like in the past people have always solved that by writing an equivalent statement. Is that true? Would you guys have said writing that exponential statement as a logarithmic statement? That's not what you guys would have done?
No, we were just doing natural log.
Oh. You would have taken the natural log of both sides, you would have logged both sides?
Yeah.
Oh, well, that's, okay, I didn't think you did that. I got the wrong impression of it. Yeah, that'd be the easiest way to do it, wouldn't it? You could write this, we know a log is an exponent, so whatever is up there is what the log has to be equal to. So you could rewrite this just using an equivalent statement. The base e log. So it's a base e log of 7 equals whatever the exponent is, right, is one way to do it. Or you could literally just take the log of both sides. And the log and the exponential cancel, and that's pretty easy, right? You get the idea? Okay. So what would I do with something like this then if I wanted to solve the log of x squared plus 1 equals 3? What would you do? Yeah, just raise each side, e to that power, right? Exponentiate both sides for the base e. Right, and those guys would cancel, and we'd have it. Okay. Then I'd have to solve a quadratic equation, but yeah, we could do that, right? Okay, so properties of logs, we reviewed these the other day, right? We said that, if you think about this in terms of order of operations from easy to hard, going from bottom to top, logarithms, they are very helpful because they drop us down one rung on that ladder. So the log of a product goes to a sum. Log of a times b is log a plus log b. Log of a quotient goes to a difference, right? Dividing to subtracting. And log of an exponential goes to a product. So that's going to drop down one rung also. So let's just practice a couple of these. Like, well, here's some we did the other day, right? We ended up with something like that. And then we didn't finish that one. So let's go further with that, right? A couple of days ago, we got stopped at the end of the class. So the first thing we did, right, was using the exponent. Log of hand cubed is just 3 times log hand. But then what can we do to the log hand? goes in the blue brackets?
If it's division and subtraction.
Okay, so division goes to subtraction, so the log of a quotient. The way we'd say that, by the way, we'd say the log of a product equals the sum of the logs. The log of a quotient equals the difference of the logs, right? And the log of a power equals the exponent times the log, right? So we're going to get on top what then? Okay. Okay, can I do anything else? You got to be a little bit careful with this. I can pull the 3 out, right? That's one thing I can do. I can take the 3 and stick that out front. Can I do anything with this one? Okay, how come, Kirk? You're right. Because it's a sum. Good. Because we got to the bottom of the ladder, didn't we? Right. Once you get down to here, there's no place for the log to go. So if you're taking the log of a sum or a difference, there's no place to go. Right. We can't simplify that. And that is the log of a difference. Right. So that's as far as we could go. Okay. Let's try. And that's something different. Okay, so let's try a couple more practice problems with that. And then I'm going to show you what the derivative of the log looks like. Okay, so how about now these? I mean, we don't need to spend a lot of time on this. Just simplify that real quick. So we call that expanding. Right, we're going to expand. We're going to take this one expression and break it up into multiple terms, simpler terms. What's it look like? So what do I do? What's the square root do? 1/2. Okay. And then log x plus, good, log y. Okay. Good. Okay. So now that's expanding. Sometimes we actually want to reverse the process. What instead, if I start you off with something that's already expanded into a sum of terms, and we want to see if we can compact this, squeeze this into one single logarithm. So what if we had something like reverse that. So write that as a single log for me, please. What'd you get? Okay, so good, we're gonna get we know we're gonna get a cube root out in front of a bunch of stuff. And what's the stuff look like?
X times quantity of X plus B squared all over X squared minus 1.
Okay, so I've got a X plus 3 squared, good, times X.
Over X squared minus 1.
And what do I need to have out in front of the whole thing? Yeah, I'm taking a log of all that out. That make sense? Okay. All right, so you got the idea. So you're pretty familiar with how to use this. It's all coming back. All right, so now the calculus. So here's the only part that's new. Everything we did there was all review. So what if we want to do this? What if we want to calculate, let's start easy, and let's calculate the derivative with respect to x of natural log x. That's what we want to come up with. Okay. So how are we going to do that? Well, here's one way we can do it. Let's define that as y. We don't know how to differentiate a logarithmic function, but what do we know how to differentiate? Well, you could know later. But what do we know how to differentiate that's related to that? Exponential, right? So we could write this in exponential form. We could either take e to the power of both sides, exponentiate both sides if we want to, or we could just rewrite that as an equivalent statement using an exponential. Either way, what are we going to get? X equals what? If I solve for x. Or if I just exponentiate both sides. Yeah, good. Everybody agree I'm just going to get e to the y equals log x, or equals x, sorry, equals x. Okay? So, now what? Okay? We could differentiate that. This is going to be a little weird. We haven't talked about this yet. This is kind of the next topic. This is called the implicit differentiation. But if I just differentiate both sides of that using the chain rule, so this will make sense. You can do this. With respect to x, what are we going to get? It's going to seem a little strange. It won't shortly. So if I take the derivative of the left side with respect to x, well, I've got a y up there, right? So what is the derivative of, there's two layers to that then, because I'm going to have to differentiate e to the hand, and then I'm going to have to take the derivative of hand with respect to x. I know that's a little strange, and you'll be much more comfortable with it in about 5 days. Right now, it's pretty new. But if I do that, if I differentiate this side, there's two layers in my chain. What is the derivative of e to the hand? E to the hand, right? So when I differentiate both sides with respect to x, on the left side, I'm going to get e to the hand times the derivative of hand. Well, okay, but we're differentiating with respect to x this time. What is dy dx? That's what we're looking for, right? That's y prime. We'll just call it y prime. Okay, what about the other side? Now I'm differentiating with respect to x. That's pretty easy. What's the derivative of x with respect to x? 1. Okay, so if I were to solve this thing for y prime, wouldn't I just get y prime equals 1 over e to the y? Okay, but what is e to the y?
X.
It's just x. Right? So what's the moral of the story then? If y is equal to the log of x, then the derivative of that, of y with respect to x, is just 1 over x. There's our derivative, new standard form. The derivative of log x is equal to 1 over x. Okay, now what has to be true with this though? If we think back to the graph of a log function, What's the domain of a log function?
All zeros.
No,
All zeros.
there's log.
Here's greater than zero.
Yeah, you can't take the log of a negative number. You can't even take the log of 0. Right. You can only take the log, the domain of the natural log function is all positive numbers, right? So we would have to include a little fine print in our contract here. We'd have to say that, yeah, this works fine, except x has to be greater than 0, right? So now we just have to chain rulify that, right? So if we wanted to do something instead, if we wanted to be more general, we want to be able to take the derivative of logs of other things other than just x. All we'd have to do is apply the chain rule. The derivative with respect to x of log u would just be what? The derivative of log hand evidently is what? 1 over hand. Times the derivative of hand, which we would just call u prime. Right? So a lot of times people would write that instead. U prime over u, right? But u has to be positive also. Okay? So what's one way, and you see it both ways. That's sometimes you don't have to really worry about whether or not u is positive, because maybe you've got a function that's only positive value for some reason, right? But sometimes you don't. Sometimes you've got bizarre functions that can be both positive valued and negative valued, right? Like for example, if we looked at the graph of a parabola. Parabolas, depending on where the vertex is and what the values of the parameters are, a parabola might have a vertex down there. And so there might be only certain intervals on that parabola where it's positive value, right? Certain intervals where it's not. And so how do you think we could ensure that we're always going to be inputting only positive values into the log function? What's a way that we can ensure that we're never going to input a value that's not positive? No? Absolute value. Yeah, so sometimes you'll even see this thing written in this form, right? Sometimes you'll even see this as the derivative with respect to x of the natural log of the absolute value of u is guaranteed to be u prime over u. Okay? They're really getting at the same point, and that is just that you have to ensure that you're only inputting something that's in the domain of the log function. Okay? So let's try this a little bit then. It's a pretty simple, it's a pretty simple derivative rule. Nothing really very complicated. So let's practice a couple of these. Okay, like so I'm going to give you a function, you tell me the derivative. Where are the implied parentheses here, by the way? X squared. Okay. So just try that in your notes and try that. What do you think, Jill? What are we going to get? The derivative of log u is what?
Wouldn't it just be like 2x over x squared?
It would. It'd be exactly
I
that.
just saw everyone like writing stuff down, and I was like.
No, that's it, right? It's u prime over u. So it's just going to be the derivative of u, so 2x over x squared. So do you notice anything? I mean, what happens if we simplify that? What do we get?
2 over x.
We get 2 over x. Yeah, that's pretty simple. Gosh, could we have gotten that a different way?
Sure. You take the top, you take x We take the 2 and move it down from the ln.
Yeah, right? You could have simplified, you could have applied your properties of logs first and made that 2 times log x, and then the derivative of log x is 1 over x times 2, right? Get that? In this case, did it make a lot of difference? Not really, not that much. But what about in something, what about this case?
Let's take it to 1.
What if I gave you one like this? And I will.
Yeah.
Okay, that looks pretty terrible, doesn't it? I mean, if you wanted to kind of just brute force your way through that, and we wanted to calculate y prime, technically, it would be the derivative of that horrible thing, and we've done problems like that within the last week, where we had to do, and they're not horrible, but they're not very fun. There's a lot of work, right? We got a power, and inside the power, there's a quotient. So there's a lot of links, well, there's 2 links in that chain, but one of the links is a quotient rule link, right? That's not very good. And then on the bottom, you've got the whole square root also. So you got a lot of simplifying to do at the end. Can you see a way to make this a whole lot easier for free? Expand it, right? Let's use our properties of logs, and let's rewrite this as what? You're all very good at this. You already told me what I need to do. 1/2 times
ln of
natural log of
top minus natural log of the bottom.
minus natural log of the bottom. Now that's an easy function to differentiate, right? So if I differentiate that, I've got my 1/2 out front. Well, what's the derivative of log x plus 1?
1 over x plus
Everybody agree? Because there's my u, right? U prime is just 1. So I get u prime over u minus
1 over x minus 1.
done.
Let's just drop the pen right. Just walk out the door.
Okay. Way easier. You see the moral of the story there, though. You want to take advantage. When you're taking the derivative of a log function, you want to maximally use those really nice properties of logs to move things down a rung when you can on that hierarchy, right? Makes the derivatives a lot easier. So let's try another one. But questions on that? Okay. So okay, try that. So how am I going to write this in simplified form? So I've got the log of the top minus log of the bottom. But what could the log of the top become? 1/2 log of 4 plus x squared. Can't go any further because it's a sum. Minus log x. So what's y prime then? So I'm just going to put the 2 on the bottom. Right? And then what's the derivative of log of 4 plus x squared? So u prime, which is what? 2x over u, which is 4 plus x squared, 2's cancel, right? Minus, that's it. Okay. Does it always work? I mean, can you always use properties of logs? Well, no, not if they don't exist for a certain problem. Like, what if I wanted to do something like y equals log of, what about log of log x? Something like that. There is no property of logs to simplify that, right? So I've just got to use the chain rule. So I get y prime equals log of u is just u prime over u. So what's u prime? What's the derivative of log x? So there's u prime over u. Everybody agree? And so if I just combine into a single fraction, wouldn't I just get 1 over x log x? And multiply, flip and multiply by the bottom. Okay? Get the idea? Okay? What about if I have something like, instead, what if I have y equals log of x squared minus 1 divided by log of 4x plus 1. Are there any properties that are going to help me there? It's not going to work, is it? Because there's no, I can't do anything to that log on the top because it's a sum or a difference. Can't do anything to the log on the bottom because it's a sum. And what we have here is a quotient of logs, not a log of a quotient, right? So there's no fancy property that's going to work there. What do I have to do? I just have to use the quotient rule, right? So see if we can crank this one out real quick. So I'm going to get low D high, right? So I've got my log of 4x plus 1 times the derivative of the top. Well, what's that going to be?
2x over x minus 1.
Right? U prime over u minus high d low. Well, that's just
4x.
right? All divided by the bottom squared. And then I'd have to do a couple things there, right? I mean, that's pretty messy, but I'm done with the calculus. That's it, right? That's all I really can do is that, and then clean it up a little bit. Okay? All right, let's call it a day.